Okay, in this video we are going to learn how to graph polar equation with the name cardioid. What is cardioid? It's graph with the shape of heart, here as you can see, right? It's with the shape of heart. And what is the importance of cardioid? Where do we use it? What for? Cardioid, I don't know if you have heard, they make cardioid microphones. And cardioid microphones are great for recording vocals and anything that is supposed to sound dry and close. Okay. Microphone is usually sensitive to sound from the front and from the rear, but they have the rejection coming for the sound coming from the sides if you use cardioid. So this microphone is a cardioid microphone. This one actually is a super cardioid because there are two of them. See, you have here two of them. This is one, which means super cardioid, right? And the big one. And as on the graph you can see here, the small one and the big one. So those are super cardioid, with which its sound is much clear, much better, and it's blocking the rejecting the noise from a side. And they are used for the large, let's say, concert halls, and where the sound of band is really loud, and so on. Okay, so cardioid can have two forms: horizontal and vertical. The equation for the horizontal cardioid is R is equal A times 1 plus minus cosine theta. And the equation of the vertical cardioid is given by R is equal A times 1 plus minus sine theta. So the horizontal cardioids are more popular because they are more effective in blocking sound from sides. Okay, so here underneath you have the R is equal A plus minus a cosine theta. I just took out A, so I think it's much clearer picture for the equation. Okay, so now once you we got the idea of how it looks like and what is good about cardioid equations and where we use it. Actually, it's not the only place where they use cardioid. And cardioid, actually, it means heart. It has shape of heart, and because it's coming from word cardiac, heart. Okay? All right. So let's graph polar equation cardioid. So we are going to graph R is equal, let me move here, R is equal 1 minus sine theta. So which means A is here gonna be 1, right? Based on this the general form of the equation, our A is gonna be 1. All right, so first let's check for symmetry. How are we going to check it? We are checking on polar axis first. checking for symmetry, polar axis. So I'm going to replace theta by negative theta. And I'm going to have r is equal 1 minus sine negative theta is equal 1 plus sine theta. Why is that? Because sine is an odd function, and let me write down here, sine negative theta is equal negative sine theta. Based on this rule, we get r is equal 1 plus sine theta. Okay, the test fails because we don't get the same, right? If we compare this one with this, it's not the same result we are getting, so it fails the polar axis the symmetry test. Let's test the next one. The line theta equal half a pi. Okay, so this is theta. Half a pi. So we are going to replace here theta, replacing with pi minus theta. All right, and the result is going to be r is equal 1 minus sine pi minus theta, and it's equal 1 minus. So sine pi minus theta, we are following the formula where it says sine alpha minus beta is equal sine alpha cosine beta minus cosine alpha sine beta, and we are going to follow this formula. Okay, so this means here, so we're getting 1 minus sine pi cosine theta minus cosine pi and sine theta, which is going to be equal 1 minus sine pi is 0, 0 times cosine theta, minus cosine pi is negative 1, right? Sine theta, and we have 1 minus sine theta. So the test is satisfying. Not on this one. Here, 1 minus sine theta and 1 minus sine theta, we get the original equation, which is satisfying. The test satisfies, is symmetric. Let me write down. Symmetric at theta equal pi over 2. Okay. Third one, testing for the pole. Okay. Or origin, right? So we are going to replace here r, we are going to replace with negative r. Okay, so then we are going to get r that is equal 1 minus sine theta is going to be equal, let me write down this way, Negative r is going to be equal 1 minus sine theta. And from here, r is equal negative 1 plus sine theta, right? Okay, the test fails. The test fails. Okay, I could write down failed the test. Failed here and failed here. Let me see if I can move this down, make a space. All right. Failed. This one symmetric, this one failed. Okay. So now let's replace theta, because regarding the pole we can use and r, replace r and theta. So we are going to replace now theta, we are going to replace with theta plus pi. Okay, and the result is r is equal 1 minus sine theta plus pi. Okay, and from here we have 1 minus, since the same sine formula, right here we have, right? So it's going to be 1 minus sine theta cosine pi plus cosine theta sine pi. And from here we have 1 minus sine theta times negative 1, cosine pi is negative 1, and plus cosine theta times sine pi, which is going to be 0. And as a result, we are getting 1 plus sine theta. This test also fails. So the graph may or may not be symmetric with respect to pole. Okay. Next, we need to identify points. So we start graphing the point. Start graphing the cardioid. So, and we are going to identify points to graph. How we are going to identify the points? Let me write down right here. Okay. Here we have, this is our theta, and this is our r is equal 1 minus sine theta. All right. So we are going to identify points on the graph by assigning values to the angle theta and calculating the corresponding value of r, just like we graph by points in a rectangular coordinate system, right? So because of periodicity of the sine function and symmetry with respect to the line theta is equal half a pi, right? Here we have it symmetric, right? It satisfies the symmetry at the point angle half a pi, which is y-axis. So we are going to assign values for theta from negative half a pi to positive half a pi. So from negative half a pi to positive half a pi. All right. All right. So, well, let's see. I'm going to use values, well-known angles, negative half a pi, And then I will use negative pi over 3, which is 60 degrees, negative 60 degrees, 30 degrees, negative pi over 6, and then 0. And from there, we move backwards with positive angles, pi over 6, 30 degrees, pi over 3, 60 degrees, and back to positive pi over 2. So it's entire range of these angles from negative half a pi to positive half a pi. So what we're going to have here, we are going to have 1 minus negative 1, because it's sine theta is equal negative 1. Here we are getting 2. For pi over negative pi over 3, we are getting 1 minus negative square root 3 over 2. This is the negative pi over 3. Sine negative pi over 3 is equal negative square root 3 over 2. Don't forget, we are all taking sine of these angles because in the formula we are using sine, right? So approximately we are going to get 1.87. And then we are getting next 1 minus negative 1 half, because sine of negative pi over 6, which is 30 degrees, is negative 1 half. We are getting 3 over 2, 1 and half, right? Next, when we have 0 degrees, we get 1 minus 0. Sine 0 is 0. We are getting 1. Okay, next, pi over 6 positive, 1 minus 1 half, because we have positive 1 half, so it's going to be equal positive 1 half. For positive pi over 3, we are going to get 1 minus square root 3 over 2, and we are getting approximately 0.13. And for half a pi, we are getting 1 minus sine 90 degrees is 1, and we are getting 0. Now, let me kind of make it more compact so it would be better to use. There we go. And this one also. And let me move down this graph so we can analyze and use the table and compare. Okay, so let's see what we have here. First of all, as we can see, polar axis, it's using 2 circles. Let me use here 2 concentric circles for measuring 1. Here is 1 and here is 2. This is why your 2 is the 2 is located here, 2 and negative half a pi. All right, let's go. Negative half a pi, r is equal to, here we have negative half a pi, r is equal to, and this is our vertical down half a pi, right? Next, pi over 3, negative pi over 3, it gets 1.87. If I zoom here, there we go. This is the point. Let me use this. It's going to be negative pi over 3. This is going to be our 1.87. As you can see, it's a little bit below than 2. That's why 1.87. And this is negative pi over 3, which is this angle. Okay, clockwise. Then we have negative pi over 6, which is 1.5. Let me see which color I'm going to use. Okay, I will use this color. Which is going to be this angle, right? And 3 over 2 and negative pi over 6, right? Third point. This one I will mark with green one. So this is our pi over 3, and this is our negative pi over 2. Okay, now moving to positive angles, when it's 0, we are getting r is equal 1, right? Which is right here, our polar axis. And this is our 0 and 1, right? Next, positive pi over 6, and we are getting 1/2. Let me zoom this better. So pi over 6, 1/2. This is going to be right here. Okay, 1/2, because if 1 is going to be 2 points, this is our 1. Where is it? This is our 2, we know. So this is our 1 is going to be on this one right here. So this is 1/2. This would be our 1, right? So this is going to be our 1/2. That's why connecting, and then we're connecting these points, right? Pi over 6, and indeed this is 30 degrees. So let me provide line. Okay, and this is going to be positive counterclockwise, pi over 6. Pi over 3 is going to be 0, 13. It's getting smaller and smaller, getting to the origin pole, right? And pi over 2, it's 0. So when we have pi over 2, it is 0. Okay, and because we found that it is symmetric when the r is replaced with negative r, so it's going to be symmetric, left side and right side. So this part we draw based on symmetry. This blue one, I'm going over with another blue one so you can see, right? There we go. All right. So this is example of cardioid. Okay, we built the graph of the cardioid ring. In this case, we built vertical cardioid, right? While we have also horizontal cardioid. Here it is. So what is the difference? In the case of horizontal cardioid, they are, that's why they call horizontal, because look here. This one is going this way, the direction, and this one direction is this way. While for vertical, this one is going up, this one is going down. This is the difference. So in our case, we built vertical cardioid. Okay. Thank you for watching, and next is going to be limacon. Limacon is more general form because cardioid is a special kind of limacon. Okay, so let's see how to build limacon, what for, where do we use it. See you in next video.